Now get introduced to the notion of multivariable calculus. So the basic object that we have to understand in order to get into the huge world of multivariable calculus is what is known as a Euclidean space. So what is a Euclidean space? So here we start with a positive integer m, and we define the m dimensional Euclidean space to be the set of all m tuples of real numbers, and we denote this set by Rm. So when we take m to be equal to 1, so then Rm is nothing but equal to R1, which is same as our set of real numbers. And the elements in multivariable calculus, the elements of R, so the elements of R are said to be scalars. And if we look at cases where m is strictly bigger than 1, then we have Rm that we have defined just above, and here the elements of Rm are said to be vectors. So scalars and vectors, you have come across these notions in physics, but let us see what these things mean in calculus. So how should we define or denote our vectors? So an element looks in Rm looks like x1, x2, xm, and I will simply denote it by underlined x. So it is as it will turn out that in most of the cases as we go ahead, I'll forget to put this underline, but I will also not expect you to write these underlines in your exams or any other assignments, as long as you understand that x denotes an element x in Rm denotes an R tuple. I will be very happy. Let us go ahead. So here we are going to mimic what we have done in our single variable calculus. So remember that we started our single variable calculus by studying what are sequences of real numbers, and here also we are going to study sequences of m tuples or vectors in m dimensional Euclidean space. And here is how this journey starts. So it is very important for us at this stage to know what are some algebraic properties, and what could be the distance between 2 points, etc. So first, some algebraic properties. So let me mention a few algebraic properties. So as I have mentioned before, algebraic properties refer to addition, multiplication, and division if it is possible in our mathematical structure. And here what we are considering is Rm. So there are a few things that I'm going to mention here. So we have this thing. So x is equal to x1, x2, xm in Rm in the m dimensional Euclidean space. Y is equal to y1, y2, ym again in the m dimensional Euclidean space. And suppose that I have an alpha, which is a scalar which lies in R1, or simply the real numbers. So what can we do about it? So do with them, so we can add them. So addition of vectors. So we can simply add two vectors by saying that okay, I'm going to take x1, x2, xm plus y1, y2, ym, and I will do exactly the same thing that first comes to our mind. We will write m tuples, and in each of the coordinate position I will write the first component plus the second component. So x1 plus y1, x2 plus y2, xm plus ym. So this is the most natural definition of addition of vectors. And then what we can do is that we can do scalar multiplication. So what is a scalar multiplication? So here I am going to take the real number that I have chosen here, alpha, and I would like to multiply this by the m tuple x1, x2, xm. You can also do this to y1, y2, ym, or in general any vector in the Euclidean space. And what is the resultant? The result is given by alpha x1, alpha x2 till alpha xn. So this process is called scalar multiplication. This process is called addition of vectors, and as you will see in one of your subsequent mathematical courses, which is called linear algebra, these two operations will give rise to a fascinating mathematical structure which is called vector space. But studying vector spaces is not uh, among the objectives of this course, and I will leave it to your linear algebra teacher for introducing you to the notion of vector spaces. So far so good, let us proceed. So as I said that we want to understand the distance between 2 points, so this leads us to the notion of norm of a vector, in Rm. So what is norm of a vector? So let x be a vector in Rm. We define the norm of x denoted by this sign. This is kind of a double modulus which we will from now on call norm of x, as norm of x is equal to x1 square plus x2 square plus xm square. So let us look at some special cases. So when we have m is equal to 1, then what do we get? Norm of x. So just let me emphasize here that here when we are going to talk about norm of a vector, then as I have mentioned that this has kind of this is somehow related to distance between two vectors, or as you will realize that this is the distance of x from the origin. We will always going to take the positive square root. So now norm of x, if m is equal to 1, and so in this case x is a real number, norm of x is equal to modulus of x, and if I take m to be bigger than 1, then I have given the formula. But let me look at this special case again. M equal to 2, then what does it give us? Norm of this element is under root x square plus y square. So that you have seen in your coordinate geometry courses in your high school, that this is exactly the distance of this point from the origin. And in particular, more generally, when you take x in Rn, this is also going to be the distance of x from the origin. Okay, so now for arbitrary m, so m bigger than or equal to 1, what is norm of 0? So the vector 0. So what is a 0 vector? A 0 vector is a vector with all the coordinates equal to 0. So this is always going to be equal to 0. And it is clear that norm of x is equal to 0 if and only if x is equal to the 0 vector. So as I have said, I will keep forgetting this underlines, and also I will not expect you to remember writing underlines every time. So let me go ahead. So let us define one more notion, which is known as scalar multiplication. So not scalar multiplication, this is called dot product. So what is dot product? So suppose you have x, y, two vectors in Rm, and you want to define a multiplication between these two vectors, and the result of this is going to be a scalar, and this is going to be given by x1 y1 plus x2 y2 plus blah 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 xm ym. Now there are a couple of very basic inequalities in terms of all those things. So two basic inequalities that we are going to make use of in time to come. So the first one is called the triangle inequality. And the second one is called Cauchy-Schwarz inequality. Cauchy-Schwarz inequality. So what do they give us? Triangle inequality says that norm of x plus y is less than or equal to norm x plus norm y, and Cauchy-Schwarz inequality that gives us that so if I take x and y and take their dot product, and if I take modulus, so here you see that there is no point of taking norm because this element x dot y is actually a scalar, and you have seen before that norm of a scalar is nothing but modulus of a scalar, and our Cauchy-Schwarz inequality says that this is less than or equal to norm of x times norm of y. Okay, so a couple of more definitions. So suppose we have x and y, two vectors in Rm. We say that x and y are orthogonal or perpendicular to each other if x dot y is equal to 0, and if x is an element of Rm with x not equal to 0. So let me take two things. So x, y in Rm such that x not equal to 0 and y is also not equal to 0. Then, so we have two vectors, then the angle, so I should use a different color to write down the different new terms. The angle between x and y to be the unique theta in 0 and pi such that cos theta is equal to x dot y divided by norm x times norm y. So please remember this formula as well. They might be very useful in your exercises and also in defining several notions later. So next we proceed. So suppose m is an integer, a positive integer, and we have x0 and x, two elements of the Euclidean space of a dimension m, and we define the distance between x and y, x and not y, x and x0 to be simply the norm of x minus x0. So if you so one thing that is clear always, that the distance is always a positive or at least a non-negative quantity. So a few more definitions. that are in order. So suppose I have been given this point x0, so let x0 be a vector in Rm. So uh, let uh, let b x0 comma r. I define the set to be set of all the vectors x in Rm such that the norm of x minus x0 is less than r. So the distance between x and x0 is less than r. So we call b x0 r the neighborhood. Now I will not write this whole word ever again, so I'll just write NBD to make you understand that I'm talking about neighborhood. So we call b x0 r the neighborhood of x0 of radius r. Now let us again look at some special cases. What do we have when we have m equal to 1? So the norm is just a modulus. So what is b of x0 r? This is set of all real numbers x such that modulus of x minus x0 is less than r. And what do I mean by modulus of x minus x0 to be less than r? This simply means that x lies between x0 minus r to x0 plus r. So this is the open interval x0 minus r and x0 plus r. What happens when we take m equal to 2? So then we get b0 px0 r is the disk consisting of x in R2 such that, so here we have to take norm of x minus x0 less than r, and if I write x as x1, y1, x0 as, I don't know, maybe a comma b, then this is same as saying that this is under root x1 minus a whole square plus y1 minus b whole square less than r. So if I have this point, so I just have to draw a circle, and all the points which are between which are inside this circle, and this point is of course AB. So all the points, so this circle is of radius r, so all the points which lie inside this circle, not on the boundary of the circle, is in bx0r. In general, when okay, so, and just one last case when m is equal to 3, so this is called this object here that I have called a disk is called a ball there, and what is b x0 r is the ball xyz in R3 such that x minus a whole square plus y minus b whole square plus z minus c whole square is less than r square. Okay, so this is mostly about norm of vector in Euclidean space, and now finally we are going to come to the notion of sequences. So let me define sequences and give you some properties like convergences, divergences, etc. before we wrap up this lecture. So what is a sequence? So now for the purpose of this course, I will mostly restrict myself to discussing the case when m is equal to 2. But many of the things that I'm going to teach you during the upcoming lectures will go through for higher values of m as well. But in your syllabus, the object that we are mainly considering is the two-dimensional Euclidean space. So what is a sequence in R2? A sequence in R2 is a map, let's say f, from the set of natural numbers to R2. So then how do we write an element of, or write the nth term of a sequence? So the nth term of a sequence in R2 is generally denoted by xn comma yn. Okay, so now when do we say that a sequence is convergent or not? So convergence of sequence, convergence of sequences. So let xn yn be a sequence in R2. We say that xn yn converges to the point x0 y0 as n tends to infinity if xn converges to x0 and yn converges to y0 as n tends to infinity. Well, nothing much. This definition looks quite simple. You do not as of now need any epsilon delta, but you may understand that the epsilon n0, the definition, or epsilon big N, however you know the definition of convergence is already inbuilt here. So in principle there are some epsilon big N which is going on, which I'm going to talk about in the next couple of minutes. Okay, so first we are going to give you an inequality. So what is the inequality? So maximum of xn minus x0 yn minus y0 modulus of those things is less than or equal to norm of xn yn minus x0 y0, and this is less than or equal to xn minus x0 plus yn minus y0. So there are two inequalities here, and let me give a sketch of a proof. So I call this inequality 1 and I call this inequality 2. So to prove 1, suppose so what we do is that, okay, so this is not a complete sentence, so this is true for all n where n is a natural number. So now here what we do is that we fix n, and as we say in higher mathematics, that without loss of generality, so this I am going to use this shorthand. If it comes again, without loss of generality, we may assume that for this particular n, xn minus x0 is bigger than or equal to yn minus y0. So what is without loss of generality? It might so happen that for some values of n, yn minus y0, modulus of that is bigger than or equal to this quantity xn minus x0, but then the same method will apply and you will come to the same conclusion. Okay, so then what do we have? So if I call this number Sn and call this number say Tn, So here what is Sn? Sn is going to be xn minus x0 modulus of that, because this is going to be the maximum. It may so happen that they are equal. In that case also xn minus x0 is the maximum, so there is no harm in writing like this. And we want to show that modulus of xn minus x0 is less than or equal to this quantity. So what is Tn? So Tn is nothing but under root xn minus x0 whole square plus yn minus y0 whole square. This is bigger than or equal to modulus of, or under root of, xn minus x0 whole square, and because this guy is always non-negative, so here this shows up. And since we are going to take positive square root always, as I have said, that this is equal to modulus of xn minus x0. Okay, and what is modulus of xn minus x0? This is exactly equal to Sn here. So as I have just mentioned, if it so happened that yn minus y0 is bigger than or equal to xn minus x0, then the same process will give you this proof if you just replace yn minus y0 by xn minus x0. So this is what without loss of generality really means. So okay, we have proved the first inequality. Now I am going to prove the second inequality, and this is really easy. This is really straightforward. I want to prove that xn yn minus x0 y0 is less than or equal to xn minus x0 modulus of that plus modulus of yn minus y0. But then what is the left hand side? The left hand side is, as I have said many times, xn minus x0 whole square plus yn minus y0 whole square. And to prove this, you can see that it is enough to show that if a, b are two non-negative real numbers, then a plus b is bigger than or equal to under root a square plus b square. But this is really trivial, since a plus b whole square is equal to a square plus 2ab plus b square, and a and b are both non-negative, so this is bigger than or equal to a square plus b square. So this proves this inequality. Basically, if you just put a equal to modulus of, or so a equal to modulus of xn minus x0 and b equal to modulus of yn minus y0. Okay, so why did we prove this? So here is something that we are going to make out of this. So the first inequality 1 said that maximum of xn minus x0 yn minus y0 is less than or equal to norm of xn yn minus x0 y0. If it so happens, so this is true for all n, and we also know that this guy is bigger than or equal to 0 always. So if xn yn minus x0 y0, if I take norm of it, this becomes a sequence of real numbers. So if this converges to 0 as n goes to infinity, then what do we have? Then maximum of xn minus x0 yn minus y0 converges to 0 as n tends to infinity. This is a consequence of sandwich theorem. So the left hand side goes to 0, the right hand side goes to 0, and the intermediate guy must go to 0 as n tends to infinity. Okay, so then what does this imply? This implies that xn goes to x0, yn goes to y0 as n tends to infinity. And what does this information imply? This information implies that our sequence xn yn converges to x0 y0. So what we have just proved is that if the real sequence xn yn minus x0 y0 converges to 0, then x and yn converges to x0, y0. Now can we prove the converse? To prove the converse, we must use the second inequality that we have obtained. And what was that second inequality? The second inequality told us that x and yn minus x0, y0, if I take norm, this is less than or equal to xn minus x0 plus yn minus y0. So if xn converges to x0 and so let me begin with this. If xn yn converges to x0 y0, then xn converges to x0 and yn converges to y0 as n tends to infinity. So this is also as n tends to infinity. So if xn yn converges to x0 y0 as n tends to infinity, then xn must go to 0 and yn must go to 0 as n tends to infinity. This is just by definition. And then what happens? Then xn minus x0 modulus of that goes to 0 and yn minus y0 modulus of that goes to 0 as n goes to infinity. And if we take summation of these two sequences, the sum of these two sequences, xn minus x0 goes to 0. So xn minus x0 modulus and modulus yn minus y0, this goes to 0 as n goes to infinity. Again, we apply sandwich theorem. We know that this guy is bigger than or equal to 0. So this inequality is true for all n. So we have seen that this goes to something. So this goes to 0 and this goes to 0. Then this must go to 0. So then by sandwich theorem, what we have shown is that modulus of or norm of x and yn minus x0 y0 goes to 0 as n tends to infinity. So what have we proved? We have just proved that our first proposition in multivariable calculus, it says that a sequence of two tuples x and yn converges to x0 y0 if and only if the norm of x and yn minus x0 y0 goes to 0 as n goes to infinity. But this is a real sequence which converges to 0. So we can now invoke our epsilon in definition. So epsilon begin definition. And what is that? We simply have to write down the equivalent epsilon in form of a real sequence an converging to 0 as n tending to infinity. So what is that? So it says that given any epsilon greater than 0, there exists a natural number n. So n depending on epsilon, sometimes we write it as n epsilon in n, such that, so this is the definition of x and yn minus x0 y0, norm of this difference, xn minus x0 whole square plus yn minus y0 whole square. This is less than epsilon whenever n is bigger than or equal to n epsilon. So this is how ideally you would like to start your definition of convergence of sequences, but we have ultimately arrived here. But the key point here is that in order to study convergence of sequences which are of the form x and yn to a tuple x0 y0, it is enough to study the convergence of these two real sequences xn and y. So whether xn converges to x0, whether yn converges to y0. So this will lead us to studying sequences of real numbers which you have done thoroughly in your calculus 1 course, and so we are not going to talk much about convergences of sequences here. So we will proceed to functions of several variables. We will look at their limits, continuity, differentiability. Whatever you have studied in your single variable calculus, we will come to the analogous forms, or in terms of functions of several variables. We will also talk about what are known as partial derivatives. We will talk about maxima and minima, so mainly local maxima and minima of the functions that we are going to consider in several variables. So more of those things in videos to come. Thank you.